So, if you think about every single square meter of the Earth's upper atmosphere,
Yeah.
right, it is basically currently being blasted by, well, about a microwave and a half's worth of just pure, unadulterated nuclear energy.
Yeah, constantly.
Right, constantly. But by the time that energy actually, makes it all the way down to your roof, it has been, it's been swallowed and scattered and battered and completely bent out of shape.
It really is a brutal journey.
It is. So anyway, welcome to the deep dive. We are so glad you're here with us today.
Yeah.
Because today we are tracing the chaotic, 93 million mile journey?
Yep, 93 million.
93 million mile journey of a single sunbeam.
And it is, it's just a fascinating progression to follow because we are taking something incredibly abstract, this massive astrophysical event, and tracking it literally all the way down to the highly engineered systems that are designed to just give you a hot shower.
Right. Which is wild when you think about it.
It is. And our source material for this deep dive today is actually a translated set of academic notes. They're titled Autonomous Heat Supply Systems with Solar Collectors.
And the why behind this entire endeavor, why we're even talking about this, is pretty stark. The notes really do not mince words about our current reality.
No, they don't.
Like relying on finite fossil fuels is just a dead end. We are looking at depleting reserves and, honestly, severe environmental degradation. So we desperately need an inexhaustible, ecologically clean alternative.
Exactly.
And I think we need to clarify our terms right away here for you listening. When most of us hear the word solar, we immediately visualize like photovoltaic panels, right?
Right, the sleek black grids on roofs.
Yeah, the ones turning photons into electricity. But that is actually not what we were analyzing today at all, is it?
Not at all, no. We are strictly looking at solar thermal energy because the data in the text clearly shows that solar energy is actually most efficiently utilized when the goal is generating hot water or warm air directly.
Okay, so skipping the middleman entirely.
Basically, yeah. We aren't trying to knock electrons loose to charge a battery. We're just trying to capture raw physical heat.
Which, that requires an entirely different engineering mindset.
Oh, completely.
Because if we were going to rely on this heat to warm our homes, we have to understand the sheer scale of the supply chain, really. And that supply chain starts at the absolute top of the sky.
The very edge of the atmosphere.
Right. And the physics here are just staggering. I was looking at the baseline numbers in the source, and there's a very specific metric we use to quantify what the sun is actually hurling at us.
Yes, it's called the solar constant.
Okay, right.
So if you position a perfectly horizontal surface at the absolute upper boundary of the Earth's atmosphere, so before any atmospheric interference at all.
It's like out in the vacuum.
Right, exactly, in the vacuum.
Yeah.
The total intensity of solar radiation hitting it is exactly 1.367 kilowatts per square meter.
1.367 kilowatts.
Yeah.
So just to visualize that, if you imagine a standard kitchen microwave running on high, that's roughly 1 kilowatt.
Pretty much, yeah.
So you are talking about a relentless, continuous blast of almost a microwave and a half of raw energy on every single square meter of the Earth's outer shield, 2047.
It is an unimaginably massive flow of power, but, that is just the cosmic baseline.
Right.
The engineering reality down here on the ground is drastically different. By the time that light punches through all the atmospheric layers and actually reaches the surface, the absolute maximum intensity you can ever hope to measure is only 1.025 kilowatts per square meter.
Wait, 1.025? That implies a massive loss right off the top.
It does.
Over 300 watts per square meter just vanish.
Oof.
Gone. And frankly, from what I read, that 1.025 number assumes a really idealized, practically mythical scenario, doesn't it?
Absolutely. It's best case scenario.
Like you only get that reading when the sun is perfectly at its zenith and the sky is flawlessly clear.
Exactly. You are only ever seeing that 1.025 kilowatts if the light is cutting the absolute shortest, straightest possible line down to the surface with literally zero clouds in the way.
Wow.
Which means for the vast majority of the planet, for the vast majority of the day, the energy hitting the ground is substantially lower than that.
So if we are losing all this power, we really need to understand the mechanics of the gauntlet it's running through.
Right.
Because I think we usually think of the atmosphere as just this, this transparent bubble.
Right, like empty air.
Yeah. But from a photon's perspective, it's more like a highly aggressive, multi-layered chemical obstacle course.
That is a very good way to put it.
Because the energy isn't just magically disappearing, right?
Yeah.
It's being actively dismantled by two main phenomena in the text,
Hmm.
absorption and scattering.
Let's look at the physics of absorption first.
Okay.
As these sunbeams travel down, they don't just passively pass through the air. They physically interact with specific gas molecules, primarily water vapor, carbon dioxide, and ozone.
And this isn't just the light bouncing off them. The light is actually being consumed.
Exactly.
I always try to visualize how a gas actually absorbs heat. It's about resonant frequencies, right?
Yes, spot on.
Like the molecules of CO2 and water vapor act almost like weights on a spring. And when infrared solar radiation hits them at the exact right wavelength, it matches their natural vibrational frequency.
That's a perfect analogy. The photon's energy is physically transferred into kinetic energy within the molecule itself.
Oh, wow.
So the CO2 or the water vapor molecule just starts vibrating more violently. It has absorbed that specific wavelength of light, converting the radiant energy into latent heat really high up in the atmosphere.
So that specific photon is just dead.
Basically, it never makes it to your solar collector. It has been permanently subtracted from the beam.
Which is precisely how the greenhouse effect works, just, I guess, happening on the way in instead of the way out.
Exactly right.
So that accounts for the light that gets literally swallowed up. But what about the light that survives that absorption gauntlet but still doesn't make a clean sprint to the ground?
Well, that introduces the second phenomenon, scattering and reflection.
Okay.
If absorption is a molecular sponge, scattering is a cosmic pinball machine.
Oh, I like that.
Because the atmosphere is suspended with countless particles, right? Water droplets, dust, smoke, and even just the nitrogen and oxygen molecules themselves.
Yeah.
When light hits these obstacles, it deflects. If it hits a dense cloud cover, a huge percentage of that solar constant is just aggressively reflected right back out into deep space as albedo.
Like bouncing off a mirror.
Exactly. But if it hits smaller molecules, we get into what's called Rayleigh scattering. And this is where the physics get incredibly elegant.
How so?
Because sunlight is a spectrum of different wavelengths, they don't all react to the pinball machine the exact same way. Shorter wavelengths, like the blue end of the visible spectrum, interact much more violently with the nitrogen and oxygen molecules in the air. The blue light is scattered in every possible direction, literally ricocheting from molecule to molecule before it finally filters down to the surface.
Whereas the longer ones don't.
Yeah, the longer wavelengths, like your red and infrared light, are much better at just punching straight through the pinball machine without hitting the bumpers.
Oh, wait. Which perfectly explains the visual evidence we see every single day.
What do you mean?
Well, when we look up and see a blue sky,
Yeah.
we aren't looking at empty space, right?
Yeah.
We are literally looking at that highly scattered, shorter wavelength solar radiation just ping-ponging through the upper atmosphere.
That's exactly what you're seeing.
And, oh wow, that also explains why sunsets are red.
Yes. Walk me through your thought process there.
Well, okay, think about the geometry of the path length. If the sun is directly overhead at zenith, the light cuts through a relatively thin slice of the atmosphere.
Right.
So the blue scatters a bit, giving us the blue sky, but plenty of the other light makes it through to our eyes. But at sunset, the light is coming in at this severe horizontal angle. So it has to travel through thousands of miles of the lower, much denser atmosphere.
The atmospheric path length is drastically increased.
Right. And over that massive distance, all the blue light just gets completely scattered away. Like the pinball machine totally filters it out.
It runs out of momentum,
But
basically.
exactly. The only wavelength strong enough to survive that long horizontal trek and actually reach our eyes are those long, lazy red and orange wavelengths.
It's a brilliant deduction. And you know, it really highlights the fundamental engineering nightmare of solar thermal energy.
Oh, I bet.
Because the intensity of radiation at the surface is inversely proportional to the distance the rays must travel through the atmosphere.
So it's constantly changing.
Constantly. Your energy supply is violently dictated by your geographical latitude, the season, the rotation of the Earth,
Yeah.
and even whether or not your local area is pumping smog and dust into the air, which, you know, just adds more bumpers to the pinball machine.
Right. So because of this gauntlet, because the light is swallowed by CO2 and bounced off clouds and scattered by nitrogen, the sunlight that finally hits the glass of our solar collectors isn't just one uniform beam of clean energy.
Far from it.
The raw fuel we are trying to capture is actually this chaotic cocktail.
It is. In thermal engineering, we actually define the total solar radiation hitting a surface as the sum of three completely distinct types of light.
Right.
And each one requires a totally different consideration. The first one is direct radiation.
Okay, so this would be the long wavelengths we just talked about.
Yeah.
The ones that survive the gauntlet untouched.
Exactly. Direct radiation arrives directly from the sun's disk at a very specific calculable angle.
It casts a shadow.
Right. It casts a hard, sharp shadow. You can mathematically predict exactly where it will be at any given minute of the year, which means you can physically angle a collector to face it.
Okay, so direct is predictable. What is the second type?
The second is diffuse radiation. This is all that scattered blue light we were just discussing, the light that was bounced around by the atmosphere but eventually made its way down to us.
Got it.
And this is where the engineering gets incredibly tricky, because diffuse light is entirely non-directional.
Right, because it's coming from the entire sky vault all at once. You can't aim a collector at diffuse light because there is no single source. The blue sky is everywhere.
Which means its impact on your thermal collector is generally the same, regardless of how you position or tilt the hardware.
Well, that sounds easier, actually.
You'd think. But the trade-off for not needing to track it is that diffuse radiation is insanely volatile. It depends entirely on atmospheric conditions.
Oh, I see.
If a thick cloud passes perfectly over the sun, your direct radiation immediately drops to absolute zero.
But your diffuse radiation might actually spike, right? Because now that cloud is acting like a giant frosted glass pane, scattering light in a million new directions.
Exactly. You're catching on perfectly. And then the third component of our cocktail is reflected radiation. Yeah, this is the light that survives the trip down, completely misses your solar collector, hits the ground or snow or maybe an adjacent glass building, and then bounces back up onto your receiving surface.
Okay, so if I am trying to build an autonomous heating system, to keep a building warm through a harsh winter, I have to rely on a fuel source that is a constantly shifting, highly unpredictable ratio of direct, scattered, and bounced light.
Yes.
It really forces you to take a hard look at the ledger here. Like, is the juice actually worth the squeeze?
It does. It requires a very sober cost-benefit analysis. But the advantages of solar energy are virtually unmatched in the physical sciences.
I mean, obviously, yeah.
First and foremost, the total ecological cleanliness. There are no byproducts, no emissions, no localized pollution.
Right.
Second, the absolute inexhaustibility of the source. And third, the complete absence of operational fuel costs.
That's the big one.
Exactly. Once the infrastructure is in place, you're capturing a raw commodity that is delivered to your property for free every single day.
But the drawbacks are severe enough to give any structural engineer a massive headache.
Oh, yeah.
I mean, the energy is strictly diurnal. It turns off completely the second the Earth rotates away from the sun.
Every single night.
And as we've just spent the last 10 minutes unpacking, it is defined by its inconsistency. You are entirely at the mercy of path length, weather, and atmospheric scattering.
You can't just open a valve and demand more heat like you can with a natural gas pipeline.
Right. Which is why the infrastructure we use to capture it has to be so sophisticated. If your fuel source is constantly playing hide and seek, your net has to be incredibly efficient.
It does. And for thermal applications, we utilize solar collectors. The absolute heart of that system is called the absorber.
And an absorber isn't just like a metal pipe painted black, is it? We are talking about selective surfaces here.
Exactly.
If I understand the physics, the goal of an absorber is to act like a highly localized, highly aggressive greenhouse.
That is exactly the mechanism. A proper absorber is coated with highly specialized materials designed to do two totally contradictory things simultaneously.
Okay.
First, it must have a massive absorption coefficient for shortwave solar radiation. It needs to look at that entire chaotic cocktail of direct, diffuse, and reflected light and trap as much of it as physically possible.
It wants to vibrate.
Yeah.
It wants to take that light and turn it into kinetic thermal energy, just like the CO2 molecules do up in the atmosphere.
Yes, precisely. But the second requirement is where the heavy engineering really comes in.
What's that?
Well, once it heats up, physics dictates that any hot object will naturally try to radiate that heat back out into the colder environment.
Sure. As long-wave infrared radiation.
Right. So a highly engineered selective coating acts as a one-way mirror. It lets the shortwave solar radiation in, but it physically blocks the long-wave thermal radiation from escaping back out.
So it's basically a thermal roach motel.
Yes.
The heat checks in, but it can't check out.
That's a great way to put it. And once you've trapped that heat in the absorber, you conduct it into a heat transfer fluid.
Like water.
Usually water, or an antifreeze mixture, depending on your climate. And that fluid physically carries the thermal energy down into the building's heat exchanger.
Got it. So you are translating the sheer chaos of the sky into a controlled flow of hot liquid.
Precisely.
Okay, but this brings me to a highly specific, honestly very curious engineering mandate that was buried in the source notes.
I know exactly which one you're going to bring up.
Because we were talking about building these incredibly complex arrays absorbers, fluid channels, manifolds, heat exchangers, right?
Yeah.
But the notes are incredibly explicit about one specific rule. It is highly recommended to design the entire system using a single material.
Yes, that mandate is completely unambiguous in the text.
And if you look around at standard plumbing or HVAC systems in like a normal commercial building, that rule seems sort of absurd.
Oh, it does. A standard boiler room is a chaotic mix of cast iron, copper, galvanized steel, brass, PVC.
Exactly. We mix materials constantly because different materials are cheaper, or they're easier to weld, or better at specific jobs. So why is the engineering protocol for a solar thermal system so draconian about using just one single metal?
Well, if you dig into the physics of it, it comes right back to the extreme volatile reality of the sun's journey that we've been analyzing this whole time.
Really?
Yeah. I want you to visualize what a solar collector actually experiences out in the real world.
Okay.
Imagine a freezing, deeply overcast morning in, say, late January. The entire collector array, the metal, the glass, the fluid inside, it's all sitting at maybe 20 degrees Fahrenheit.
So it's ice cold and physically contracted.
Right. Then suddenly a fast-moving weather front pushes the clouds away.
Oh, wow.
In a matter of seconds, that entire array goes from deep shade to being violently bombarded by intense direct solar radiation. And those selective coatings we talked about, they do exactly what they were designed to do. They trap that heat immediately.
Oh. So the temperature of the absorber skyrockets from 20 degrees to maybe, 200 degrees in minutes.
Exactly. It's an intense thermal shock. Now, consider the thermal expansion coefficient of different metals.
Ah.
Copper expands at a significantly different rate than steel or aluminum when subjected to identical heat.
Right.
So if you build your absorber out of aluminum, but pipe it into a copper manifold and weld them together,
Well,
what happens during that rapid temperature spike?
they fight each other.
Violently.
The aluminum expands faster and further than the copper.
Yeah.
The sheer mechanical stress at that joint would be catastrophic.
Yes. Over thousands of heating and cooling cycles, clouds passing, day turning to night, that joint is going to suffer severe metal fatigue.
It'll just warp, crack, and eventually hemorrhage all the transfer fluid.
You've got it. The structural integrity of the system simply cannot survive dissimilar expansion rates under such aggressive, localized thermal shock.
Wow.
But here's the thing. The mechanical stress is actually only half the problem.
Wait, there's more?
Oh, yeah. The single material rule is also preventing something even more insidious. Galvanic corrosion.
Okay, galvanic corrosion.
Yeah.
Wait, this is what happens when you accidentally build a battery inside your plumbing.
That is literally exactly what happened.
Really?
Yes. Whenever you connect two dissimilar metals, say a copper pipe and a galvanized steel fitting, and you introduce an electrolyte.
Which in this case is the hot water flowing through the system.
Exactly. You have inadvertently created a galvanic cell.
Because the metals have different electrical potentials.
Yes. One metal acts as the anode, and the other acts as the cathode. The less noble metal, which is usually the steel or the aluminum in this scenario, will begin to literally sacrifice its own electrons to the more noble copper.
Oh, jeez.
And the hot water acts as the perfect conductive superhighway for those electrons to travel.
So the hot water is physically stripping the steel apart at a molecular level just to feed the copper.
Exactly. And because solar thermal systems operate at significantly higher and more fluctuating temperatures than your standard domestic plumbing, the kinetic energy in the water accelerates this chemical reaction exponentially.
So it happens way faster.
Way faster. If you mix metals in a solar loop, the anode metal will just dissolve into a pile of rust and scale from the inside out in a fraction of its normal lifespan.
Wow.
So the single material rule exists because harnessing the unpredictable, chaotic power of a nuclear furnace 93 million miles away, it requires absolute structural and chemical harmony down here on Earth.
Right.
If the sky is volatile, the metal must be perfectly unified.
Man, it's incredible when you frame it like that. You basically need a perfectly tranquil, monolithic container to hold a perfectly chaotic fire.
That's beautifully said.
It really recontextualizes the entire process for me. I mean, we started by looking at a constant, unyielding blast of 1.367 kilowatts up in the frozen vacuum of space.
Yeah.
And we tracked it as it smashed into the atmospheric pinball machine, getting absorbed by vibrating gas molecules, bouncing off clouds, and scattering into the beautiful blue sky.
It's quite a trip.
And then we watched the surviving cocktail of direct and diffuse light get trapped in a localized greenhouse on a roof.
The Roach Motel.
Right. And finally, we see how the violent temperature swings of that captured light dictate the very molecular chemistry of the pipes we use to carry it inside.
It is just a profound chain of cause and effect. The physics of astrophysics seamlessly bleeding into the physics of localized plumbing.
It really is. Well, thank you so much for taking this journey with us today, tracing the sunbeam all the way down to the thermal expansion of a copper pipe. But, for you listening at home, if you think about the implications of that single material rule, it leaves you with a pretty staggering thought.
How do you mean?
Well, if our small, highly engineered solar arrays require such perfect, unyielding material harmony just to survive the daily thermal shock of the sun's chaos, how are the materials in our massive mixed metal infrastructure, our suspension bridges, our steel and glass skyscrapers, our concrete highways, quietly battling that exact same relentless thermal expansion and contraction and every single time the sun comes up?
That is a terrifyingly good question.
Right. So keep questioning the world around you, keep looking up, and we'll catch you on the next deep dive.